Okay, so in this video, we'll look at combinations. Last video we looked at permutations, and they're closely related with one slight difference in why you would use one or the other. So let's dive right in. First off, combination. What is a combination? So, a combination is let's not say A, is one possible group of elements. The important thing about a group, as opposed to a permutation, which is an order, is in a group, order does not matter. So, the difference is this. In one situation, a permutation situation, I could say, in a race of 8 people, how many ways can you get a first, second, and third place finisher? That's a permutation. There's a first, there's a second, there's a third, there's an order to them, they're not interchangeable. However, if I said out of a class or a set of 8 people, how many different ways can I form a group of 3? Since no one in the group is greater than or less than, there's no order to the members in the group, that would be a combination. And the number of combinations which is what most of the problems will ask you about for this, is the number of distinct groups. Now, this does not mean that if I have 10 people, how many combinations of 2 can I get? That doesn't mean 5, because I could split 10 into 2 5 times. It's a very different question. So let's look and see how the formula works, make sure we have this straight. So NCR or CN comma R, or this notation with this N over this R, are all ways to figure out the number of groups of R from a total of N elements. Now, I usually use this notation here when I'm writing it, however they're all equivalent. In the permutation, I forgot that a lot of books use the P, N comma R notation. It's the same thing as NPR from there. This notation is used, I've seen it used by a lot of my professors later in my college when they're using combinations for other things. You should be familiar with all of them. So here is the formula. Whichever format you write, I'll write it this way. NCR is going to equal n factorial divided by n minus r factorial. And at this point, this is the permutation formula, the NPR formula, times r factorial. So, verbally, what's going on here? Well, at the top, this is the way to permute all of the elements. At the bottom, this here sort of gets rid of elements not in the group. I'll explain what I mean by that in a numerical example shortly. And this R gets rid of order, because in combinations, order does not matter. So, a couple examples. 7, let's rewrite it in this one. 7c3 is going to be 7 factorial, and that's the way to line up 7 objects. 7 minus 3 factorial. This here is going to get rid of the objects that aren't in our group, and then times 3 factorial. Now, let me show what's going on. So 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. 7 minus 3 is 4. 4 factorial is 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. And let me look at it this way. So in 7c3, I'm finding groups of 3 out of the 7 total. So when I start off with the 7 factorial, well, that's how many ways to permute all of them. Order is mattering. We have way more elements than we're actually considering. The 4 factorial here, which was from n minus r, is what tears this off, gets rid of this. It's going to cancel out 4, 3, 2, 1, top and bottom. And then the last part, the 3 factorial, that is what takes care of getting rid of order. Since we have 3 elements here, and this is a permutation, it keeps track of order, I want to get rid of order, so the number of ways I can permute these 3 elements is 3 factorial. And I always sort of work it out this way. I cancel out as many as I can, whether the bigger number is here or here, I cancel that out. So in this case, 7 minus 3 was 4, so the 4 factorial cancels out more stuff to begin with. If I had 7 minus 2 here, then this would be, if I had 7 minus 5 here, this would be a 2, and this would be a 5 factorial, and then I'd cancel out with the 5. And the next thing I do is this. So at this point, I'm left with, sorry about the little sloppy work here, I'm left with 7 times 6 times 5 over 3 times 2 times 1. And before I multiply all of this out, I notice, okay, 3 and 2 and 1 I can cancel out here. 3 times 2 is 6, times 1 is 6. So that's going to be 6. And the 6 over 6 cancels out. And I'm left with 7 times 5, which is 35. You could also do this in the calculator. It's similar location to the other things. So I start off by putting the first number, 7, math, go over to probability, and CR is the third thing down there. 3, and if the calculator works correctly, which it does, I get 35. Okay. So let's look at a real-world example. In a class of 25 students, how many ways can you form a group of 3 students? Since I'm actually forming groups here where order does not matter, it's going to be 25C3. And I said I'd talk about more how to understand this. I'm not saying that I'm seeing how many groups I get if each group has 3 students. That would be 25 divided by 3. This is saying I'm making a single group of 3. I want to see how many different ways that can be made. So let me figure out this value. So we know that's 25 factorial over 25 minus 3 factorial times 3 factorial. You could use the calculator. I'm just going to do a little bit of work here because perhaps you're in a class where you can't use the calculator. I see that this 22 is bigger down here, so I can cancel out the 22 with a lot of the stuff here. 25 is 3 bigger than 22, so at the top I have a 25 times 24 times 23, and that's going to be times 22 factorial. Don't even need to write that once you get good at this. Over 22 factorial times 3 factorial. You can see the 22 factorials cancel. And now it's very workable. 3 factorial is 6. And I have the 24 over 6, which is 4. So I end up getting 25 times 4 times 23, and it works out really nicely. 25 times 4 is 100, times 23 is 2,300. Calculator will give you the same answer, no problems there. And so just so we're clear, if, let's say that each student is a letter from A to Y, one possible group is A, B, C. One possible group is A, B, D. One possible group is A, B, E. Notice, I'm not making groups because then this would have two of the same kids in each of these groups. I will not consider the group B, A, C because these are the same group. They're made up of the same people. So that's not an additional group. That's what this right here gets rid of, is these repeats. These three letters can be repeated that many times. So that's why we get such a large number, even though someone's saying, wait, if I have 25 kids and I split them into groups of 3, I can't get 2,300 groups. No, that's not what this is asking. All right. An interesting thing here. So NCR1 and NCR2, sometimes you can have the same value with different sized groups, and this is why. So let's consider this. If I had 7C2, that's going to give me 7 factorial over 7 minus 2 factorial times 2 factorial, which is going to be 7 factorial over 5 factorial, 2 factorial. And in here, these two bottom numbers will always add up to n, because you have n minus r and an r. They better add up to n. And here's what can... I guess another thing. You will never get a decimal out of this. When you divide out both of these factorials, you'll always be able to divide it out. The reason why is a little bit trickier than I want to go into just now, but it has to do with the multiples of both of these still being in after one of them cancels out. Okay, but here's the thing. 7 factorial over 5 factorial 2 factorial is the same thing as 7 factorial over 2 factorial 5 factorial, multiplication being commutative. And so, isn't this the same thing as 7 factorial over 7 minus 5 factorial 5 factorial? Which is 7C5? So what's going on here? How did we get the same thing for 7C2 and 7C5? Why are these the same, and what's happening? And the reason is this. If I have 7 elements, and I choose groups of 2, when I choose a group of 2 elements, or if I choose 2 elements to be in my group, I'm also effectively choosing 5 elements to be out of the group. So this is actually the same as choosing 5 elements to be out of our group. So back to this example up here where I have NCR1 and NCR2. If I have these two things here, NCR1 equals NCR2 when R1 plus R2 equals N. Or you could do it a different way. You could say R1 equals N minus R2, or any way to solve this. R2 equals N minus R1, because when I'm choosing a group of R1 elements, then I have N minus R1 elements that I'm choosing to be out of the group. And that's what's going on here. So here's an example. This one is related to the binomial theorem. I'll get more into that in a different video. But here's the idea. So if I'm expanding this, and I don't know Pascal's triangle or the binomial theorem, what I would end up doing is multiplying x plus 7, or sorry, x plus y to itself 7 times. So 5, 6, 7. Okay. Now what actually happens here is, because of how you distribute or FOIL or area model or whatever for this, each one of these factors is either going to be an x or a y when it works in here. So this could either be x or it could be y. If all of them are x's when I'm multiplying, then they'll give me x to the 7th, and there'll only be one way to get that. When I have 3 of them x's and 4 of them y's, that's where I'll get x cubed y to the 4th. And notice, I can't have 3 x's and 3 y's because I need to have all 7 of them accounted for. And the idea is this: if I want x squared y to the 5th, that will happen 7 for 7 factors, choose 2, because I want to choose 2 of these to be x's. 7 choose 2, 7 factorial over, we saw this last slide, 7 minus 2 factorial, 2 factorial. That's going to be 7 factorial over 5 factorial, 2 factorial. I'm going to cancel out sort of the 5-ness in here. So 7 is 2 bigger than 5, so I'll be left over with a 7 times 6. And divided by 2 times 1. And again, I'm not going to multiply 7 times 6. I'm going to divide 6 by 2 first, and just get 7 times 3, which is 21. So the coefficient on this will be 21. That's part of the binomial theorem. And this will be the same as, instead of choosing 2 elements to be in the set, so 7C2, it's the same as choosing 5 elements to be out of the set. And this is going to lead me to know that the coefficient of this, so the coefficient, not cof, coefficient of x squared y to the 5th will equal the coefficient of x to the 5th y squared. All right, last case is where combinations can get a little bit harder. They're just more steps. When I need to make multiple choices, choose multiple things. And the big example I have is sort of picking hands of cards, and I'll put up a bunch of examples. That's actually going to be a third video in this sort of lesson, where I'll go through all of those probabilities, all of those counting rules. But all you're going to do is sort of make the category choices then choose inside the categories. Now, for all the card problems, I'll use this notation, this sort of purplish color for category choices, and then choosing the specific things inside those for blue. So let's dive into an example here. In how many ways can you get 2 pair in a standard 5-card hand of poker? And so there are 13 different card types, 4 different suits, so 4 of each card type. And so I want 2 pair. Well, I'll start off by taking my 13 cards, or 13 card types, and choosing 2 of them to be the pairs. In each of those cards, so once I've chosen, let's just say that I chose an ace and a 4. There are 4 aces in the deck, and I need 2 of them in my hand to get a pair. And I think it's an ace and a 4. There are 4 4s in a deck, and I need 2 of them to be in my hand. And then I need to make sure that the last card is not paired up to one of these, or else it'll actually be a full house. It'll be too much. So I've chosen 2 of these to be to be the pairs, 2 of the card types out of the 13, so I need to have one of the remaining 11 card types. So if this is an ace and a 4, it has to be something different. Let's say a 7 or an 8, but it can't be an ace or a 4. Sorry, not choose 2, choose 1, because I only need 1 additional card type in here. And from that, I will choose 1 card. So let me list this through. This here is to choose the type of the pairs. These are to choose the specific paired cards, making sure you get 2 of that card and 2 of that card. This is to choose the type of the lone card. I decreased this to 11 so that I don't get one of the 2 cards we already had a pair of. And this is to make sure that we choose the specific lone card, one of the 4 that's actually in there. When I do the computations, I already did them. It'd be a little pain to put in the calculator, but you get through it. When I do that, I should end up with getting 123,552 possible ways to get 2 pair in a standard 5-card hand of poker. Alright, I'll follow this up with some examples, and then I'll follow up with a 3rd video dealing with all of these poker problems, from getting nothing in a hand of poker all the way up to the royal flush.